Before 2017, machines translating language were bound by a strict constraint. They read text like we do, moving word by word, left to right. Take a look at this animated diagram of a recurrent neural network, or RNN. As it processes a sentence, it generates a sequence of hidden states. Each step relies on the previous state and the current word, forcing nodes to process in an unyielding order. Reading in strict chronological order creates a severe memory flaw. By the time an RNN reaches the end of a long paragraph, it often drops the context from the very beginning. This sequential nature also creates a massive computational bottleneck. Because the system has to finish processing step 1 before it can start step 2, it is impossible to process multiple training examples simultaneously. Reading time-step by time-step capped machine efficiency and kept true contextual understanding out of reach. Researchers tried fixing this memory decay by stacking intricate encoders and decoders with early attention mechanisms. They applied factorization tricks and conditional computation to speed things up. Even with these complex patches, the core constraint of sequential processing remained. Advancing artificial intelligence required replacing the foundation of chronological sequence. In 2017, researchers at Google proposed a model architecture that discarded recurrence altogether. They asked what would happen if the machine looked at every word in a sentence at the exact same time. They called their solution self-attention. Instead of processing a sentence step by step, self-attention instantly calculates the relationship between different positions within a single sequence to compute a global representation of the text. This visual comparison highlights the difference. A traditional sequence takes a linear path, traveling point to point. Self-attention requires a constant number of operations, acting like a web that instantly connects a central node to all surrounding nodes. The physical distance between words in a sentence was no longer a barrier to the machine mapping their relationship. By charting global dependencies instead of chronological order, the machine stopped translating individual words and began processing holistic ideas. We can see how this works by looking at anaphora resolution, the ability to know exactly which noun a pronoun refers to in a complex sentence. This research document plots the test sentence. The law will never be perfect, but its application should be just. Older sequential models struggle to associate its with law. Multi-head attention solves this instantly, assigning parallel mathematical weights, bridging the pronoun directly to the noun. The transformer traces the structural and semantic web of human language, identifying relationships that simple proximity would miss. This diagram details the complete transformer architecture. It stacks these multi-head self-attention layers into an encoder-decoder structure, dispensing with recurrence and convolutions entirely. Removing these sequential constraints provided an immediate computational benefit. The transformer could process massive datasets in parallel across multiple GPUs. This data visualization illustrates the results on the WMT 2014 English to German translation task. The model achieved a record-breaking BLEU score of 28.4, outperforming all existing single models and ensembles. The big model reached this state-of-the-art translation quality after training for just 3.5 days on 8 GPUs, a tiny fraction of the time required by its predecessors. The transformer's capabilities applied directly to other challenges. It successfully tackled complex structural tasks like English constituency parsing across both varied and limited datasets. The researchers didn't create a more capable machine by adding layers of complexity. They achieved it by stripping away outdated mechanisms until only attention remained. By breaking the sequential bottleneck and proving machines could process entire contexts simultaneously, this single architecture built the foundation for the generative AI models in use today.